I'm Grandmaster C. You see me in such fine quality educational videos as "My lab coat's on fire. What do I do now?" and "Honey, I blew up the lab." Today we're going to be looking at equilibrium. And this is just an introduction. Nothing more, nothing less. But we need to get into it, so let's go with it. So when we think about equilibrium, we know that reactions are reversible. A plus B gets us C plus D. That's our once upon a time, happily ever after. There's our forward reaction. We go forward. We go on to UCLA, for example. But then there's the other side of the coin, that reactions can be reversible. Not all of them, but some can. C plus D goes back to A plus B. That's a reverse. We're going to USC! Yeah. Now, originally, the idea is that if there's only A and B at the beginning, only the forward reaction is possible. You're not going to get a backwards reaction. You won't have a reverse reaction until C and D build up. That's the idea. Now, the idea about equilibrium, that the rate of going back and forth, I whip my hair back and forth, I whip my hair back and forth, that it comes and it's equal. That's the idea when we talk about rates. Okay? Now, when we look at it in a graphical perspective, here is your increase, here's the reaction rate over time. That at the beginning, the reverse reaction is going to be 0 because you don't have any products. Okay? And here you got all the stuff here for our reactants, our ingredients. So it's going to follow that over time that the lines are going to slowly get together. And then eventually they're going to meet, where they come to an equilibrium where it goes back and forth. Okay? And that's the general idea with this. Now, what is exactly equal at equilibrium? Well, for one thing, the rates are equal. Now, the concentrations, they may or may not be. Highly unlikely that they're going to be. Okay? But the idea is that we look at the rates, there's two things that are going to tell us. One, the concentration of the players involved, and two, the activation energy. Okay? At some point in this video, I'm going to hold up a couple of signs. And you're going to have to follow what those signs do on your paper, if you want to get the credit for it. Okay, so rates are determined by concentrations and activation energy. Concentrations don't change at equilibrium, or if the reaction is really, really really slow. Okay. So we have a formula, and here it is. The equilibrium constant, the big K. Not quite the same as the little k that we did in the last chapter when we were looking at kinetics. This is going to be a big K. This is more important. Okay? So the equilibrium constant, if we look at this reaction, 2A plus 5B, it goes back and forth to get 3C and 4D. So our big K is going to be the concentration of all the products divided by the concentration of all the reactants. Okay, what does that mean here in this equation? Well, K is going to equal the products, so that's 3C, so that's going to be the concentration of C to the third power, taking into account this, times the concentration of D to the fourth power, taking into account this, divided by the concentration of A to the second power, times the concentration of B to the fifth power. So, okay, what difference does the K make? Well, what the K will do, ladies and gentlemen, if the K is huge, then the products are favored. In other words, we're going to be shifting more products are being made. Actually, I should go this way. The products are going to be made, more products. If the K is huge, it's going to be. Now, we notice that if you look at solids and liquid waters, we assume they have constant concentrations. So we really don't take those into account here for a reaction like this. Okay, law of mass action. So for any reaction that we have, we can look at A and B, JA and KB gets us LC plus MD. We can look at the rate constant here. As you can see, products to the power divided by reactants to the power. K is what we call our equilibrium constant. And that back and forth arrow tells us that, hey, the action is The reaction is reversible, okay? That would be kind of an important thing. Now, we can talk about playing with K, okay? Oh, let me go back here for one moment. When we look at the law of mass action, that's what they're talking about. They're talking basically about this law of mass action where we can get our equilibrium constant. Okay, this is our equilibrium constant here. This is what they are referring to when they say the law of mass action. And it's a law, it's not a theory, and it's not a hypothesis. Now again, we can play with the K here, and if we write the reaction in reverse, ladies and gentlemen, okay, where now it's flipped, we're going to have a K prime, because we're going to have a new equilibrium constant. Now, the fact is that the thing goes backwards. If it's going backwards, the value of K is going to be different. In fact, if you were to go and plug this in, you're going to find that the value, it's 1 over K. So the new K, or K prime, if you will, is basically the inverse of the original K. Now think about it, that makes sense. Okay? If my equilibrium constant is 2 for making products, and if I'm now going backwards, it's going to be 1 over 2. That's the general idea. That would be an example of it. Now, on the other hand, if we look here and let's say we multiply the equation by a constant, NJA plus NKB gets us NLC plus NMD. We use a constant like N. Doesn't matter what N is, it's some miraculous number. Okay, then when we go through and look at the equilibrium constant, and here is plugging all this in, what you're going to get, this new K prime, if you will, is going to be K to the nth power. Okay? That's what it's going to be, which is really nice. It kind of makes it simple in that. All right? Now, when we look at it, ladies and gentlemen, when we look at this, we look, okay, that's fine, here's our K prime, and if we bring it up to a factor of N, well, that's what our N is going to look like, okay? So we're going to have now our units for K, and well, what exactly are the units of K? That's just it. They're not really specific because it really depends on several things. It depends on the various powers and the units of concentration that we have. So, I mean, you can have something that's cubed in one equation. You can have something that's squared in another. Or it could be to the 4th power or the 5th power. It depends on the reaction. So don't get hung up on K and the units. Don't really get hung up on it. Now, of course, again, they depend on the reaction. Okay? Very important idea here. When we're looking at a chemical reaction that's at equilibrium, the K is constant at any temperature. Okay? The K is constant at any temperature. The temperature affects the rate, though. Okay? The equilibrium concentrations do not have to be the same. Only the K will be the same. And here's an idea that's important. Equilibrium position is a set of concentrations at equilibrium. We can have different equilibriums at different temperatures. But the constant itself, the K, doesn't change. That's a cute big thing. Big deal. Okay? Equilibrium constant, okay, 1 for each temperature. So let's take a look at this one here for a moment. So if we go and calculate K for this example here, and if you look at it, there's something that you're going to notice. You're going to notice, ladies and gentlemen, that if you try to calculate K with the initial, you're not going to get anything. And why aren't you going to get anything? Well, when you plug in, if our formula is K is equal to concentration of our products over the concentration of our reactants, here's our product at the initial. It's 0, and you're not going to be able to figure it out, and you're going to sit there and feel foolish because you spent your time on it. Okay, so don't do that. What you are interested in, when we say calculate the K, we're looking at our equilibrium right here. Here is the equilibrium. So, what is that going to look like? Okay, well, given the formula that we have, ladies and gentlemen, we look at this, and I'm going to go ahead and I'm going to draw it here. Okay, we know it's going to be products over reactants, so I know that my product is going to be 0.921, and that, ladies and gentlemen, is going to be cubed. It's going to be cubed because of this coefficient here. And then we are going to divide it by our reactants. Well, what's our reactants? Our N2 and our 3H2. Well, our N2 is going to be 0.9. Oh, wait, I made a mistake. Hold on. Let's go back. We look at product over reactant. I'm sorry, guys. It's 0.157. And that is cubed over. So there's our product. This is what they gave us at equilibrium. That's when they says, I whip my equation back and forth, I whip my equation back and forth. It's the same. So here we have N2, that's going to be 0.921 multiplied by 0.763. Okay, and that's going to be also cubed because you've got your coefficient here as well. So this is what it would look like when you are calculating your K. Now, I'm not going to figure all that with you. I'm going to give you guys the answer. It's basically 6.02 times 10 to the minus 2. That's the value of K for this particular chemical reaction. Okay? All right. Any questions on that? All right. Okay, as we are moving on here, okay, let's move on. So here's another problem that we look at. We look at calculate K here again. We're going to do the same thing, except now this is a little bit different, and we're going to go ahead. Again, it's going to be product over reactant, so I'm going to write it over here. So K is equal to product over reactant. So we're going to do the same thing here, okay, and you're going to find that let's see, 0.203, that's going to be cubed over 0.399 multiplied by 1.197, and that is cubed. And guess what? Your final answer is going to be 6.02 times 10 to the minus 2. And guess what? K is the same. K is the same. Yeah, K is the same. No matter what the amount of starting materials you have, K is the same. But did the equilibrium concentrations remain the same? No. No, they did not. So that's just proving a point how K is constant throughout the reaction. Okay? So that's what we got. So now we know that the K is going to be constant when you're dealing with the chemical reaction. That's there. Okay? Mr. Canu's favorite color is blue. All right, equilibrium and pressure. Now, yeah, we got some of the reactions out there. They are going to be gaseous. So we're going to use our good old Selfie gas law, PV equals nRT. Now think about it. If we want the pressure by itself, we could divide both sides by V. So we got N divided by V times RT, or N over V, moles over volume. Oh my gosh, we're talking about concentration, molarity. Yeah, molarity. So P is equal to our concentration times RT, or C is equal to P divided by RT. That's our equilibrium and pressure. Now, we can figure out a constant for the pressure along the same lines. It's the same thing where you get your product divided by your reactant and raised to whatever the coefficient is. Raise it to that power that you have here. Excuse me. All right. as we're moving along here for equation, equilibrium, and pressure. So if we look at K, and we're looking at the ability to find the concentration, this formula would represent concentration. But we're looking at the pressure divided by RT, and again, squared. Why? Look at the original equation, and we did the same thing down here. Okay. Now we can separate the 1 over RTs, okay, and we can divide those out, and what we got, K is equal to the K of the pressure, okay, times this, which is equal to Kp times RT. So we can take the constant divided by RT, and we'll get the constant pressure if you have the concentrations of it. Okay? Holy mother of humanity, general equation. Yeah. Okay. This one's a little bit messy. Okay? And what you got here is you've got your original equation, JA plus KB gets us LC plus MD. All right? And we have here our constant, our pressure constant. Well, that's pressure of C to the L power times pressure of D to the M power, okay, divided by PA to the J power and pressure B to the K power. Okay, we're not doing anything new here. What we're doing is we're looking at the constant for the pressure, and we're plugging in the pressures of this. This is only true if all of them are gases, because if there's any solids or liquids, that kind of changes things. So this is all gases. So what is pressure? Well, pressure is equal to concentration times RT. So we can substitute that in there as well. And now we can go ahead and we can multiply this all the way through. And the bottom line is, ladies and gentlemen, our constant for pressure is equal to the constant times RT to the L plus M minus J plus K power, or K times RT to the change of the number of moles of gas that you have, where delta N is equal to the change in the moles of gas. And we'll get to that in there, okay? And for this, ladies and gentlemen, we are going to stop here, okay? I wanted to cover a lot of stuff with you guys, and I wanted to get you guys on a jump start. So for equilibrium, you're looking at a major formula that's going to be consistent throughout the entire chapter, where K is equal to the concentration of the products divided by the concentration of the reactants. Now we do raise them to whatever power that needs to be based off of the coefficient that's in the original equation. So we can do this for aqueous solutions. We can do this for gas solutions. Okay? If it is a solid, we do not count the solid in this. We just don't. All right? And with that, ladies and gentlemen, I am going to stop here. Again, I gave you guys a few clues. I showed you some papers that you needed to write down the information on, because not everybody got the exact same information. And you're saying, wait, I missed it. Guess what? You'll have to replay it again. But I am on YouTube, and again, this is it. I'm Grandmaster C. I'm signing off, and I will see you in the later. Hasta